Hi everyone, welcome to lecture number 5, numerical problems on economic load dispatch. In the previous lecture, we discussed about optimal operation without losses, that is nothing but coordination equation. So let me write that equation for you just for a quick revise. So the coordination equation is nothing but the incremental fuel cost of all the units should be same. So that is nothing but dc1 by dp1 is equal to dc2 by dp2, that is equal to, and so on up to dcn by dpn, that is equal to lambda. So that means if there are n number of generating units in any power plant, the condition for optimal operation without losses is the incremental fuel cost of all the units should be same, and that should be equal to lambda, where lambda is called as Lagrange multiplier. Whenever we consider the losses, then the condition will become exact coordination equation, and that is given as dc1 by dp1 into L1, that is equal to dc2 by dp2 into L2, and so on up to dcn by dpn into ln, that is equal to lambda, where L1, L2, and so on up to Ln are called as penalty factors of n number of generating units. So here L1 can be expressed as 1 by 1 minus dou PL by dou P1, where this 1 by 1 minus dou PL by dou P1 is nothing but ITL, incremental transmission losses. So similarly, L2 can be expressed as 1 by 1 minus dou PL by dou P2, that is equal to 1 by 1 minus ITL of second unit. So previously this is ITL of first unit. So similarly, you can express Ln is equal to 1 by 1 minus dou PL by dou Pn, that is equal to 1 by 1 minus ITLN. So here PL is called as power transmission losses, and that can be expressed by using loss coefficients or V coefficients. We have seen the derivation of loss coefficient from loss formula in the previous lecture. So PL can be written as B11 P1 square plus B22 P2 square plus 2B12 P1 and P2, where B11, B22 and B2, B12 or B12 is also equal to B21. So all these are called as loss coefficients. These are called as loss coefficients or B coefficients expressed in per megawatt or megawatt inverse. So all these conditions we have seen in the previous class or previous lecture, and we have also done one numerical example problem based on the coordination equation. In this lecture, we are trying to solve so many problems by using all these equations. So let's try to understand how we can implement these conditions in solving the economic load dispatch problem and in determining the individual units power values such as P1, P2, and so on up to Pn And once you determine the individual units power values, you can also find the transmission power loss PL, and then you can also find how much power will be delivered to the load demand, that is nothing but PD. So in this particular slide, you can have all the important conditions or equations with respect to economic load dispatch. So maybe you can give a numbering for all this. This is the equation 1. So the equation 1 represents the condition for economic load dispatch by neglecting the transmission losses. And this particular equation, if you treat this as equation 2, so this equation 2 represents the condition for economic load dispatch by considering losses. So where the penalty factors of each and every unit are incorporated in the condition. So the penalty factors can be determined by using these equations. So in a simple manner, we can represent penalty factor is equal to 1 by 1 minus incremental transmission loss of that particular unit. And this incremental transmission loss is given by derivative of transmission loss with respect to that particular unit power output. So if you want to find the incremental transmission loss for unit 1, then you have to differentiate with respect to P1. And if you want to find the incremental transmission loss of unit 2, then you have to differentiate with respect to the power output of unit 2, that is nothing but P2. So and so on. So here the transmission power loss PL can be expressed by using B coefficients using this equation, where PL is equal to B11 P1 square plus B22 P2 square plus 2B12 P1 P2. So here B11, B22 and B12 are called as loss coefficients, or these are also called B coefficients. B coefficients. And all the B coefficients or loss coefficients are expressed in the unit of per unit megawatt or per megawatt or megawatt inverse. So now let's try to solve some of the numerical problems by using all these equations. So the first numerical problem is given here. A two-bus system is shown in the figure. This is the figure. If a load of 125 megawatt is transmitted from plant 1 to the load, a loss of 15.625 megawatt is incurred. So try to understand this statement. A load is connected here near to the plant. So 125 megawatt of power is transmitted from plant 1 to the load. So here this is the plant 1 and this is plant 2. So plant 1 power output is indicated as P1, plant 2 power output is indicated as P2. So from plant 1 to towards load, there is a power transfer of 125 megawatt. So during that power transfer, as the load is located very far from the plant 1, there is some loss taking place in the transmission line, and that loss is nothing but 15.625 megawatt. So out of 125 megawatt of power, 15.625 megawatt of power is being wasted as power loss, and the remaining power will be delivered to the load as per this given problem statement. Now determine the generation schedule and the load demand if the cost of received power is rupees 24 per megawatt hour. So whatever the cost is given here, this is nothing but lambda value, Lagrange multiplier. So this lambda is nothing but 24 rupees per megawatt hour. Now we have to determine the generation schedule. So here we have two power plants connected in the power system. So determine the generation schedule means we have to determine the individual units power outputs. We have to find what is P1 value, and also we have to find the P2 value. And once you find P1 and P2 value, you also need to find what is the power demand, that is PD value. Solve the problem using coordination equation and the penalty factor method approach. So we have to solve this problem by using two approaches. One is by using coordination equation, what we have seen in just a few minutes back in the previous slide. And also we have to use penalty factor method approach. So actually speaking, both coordination equation or penalty factor method are same. Only the way how we represent equation is little different. So other than that, the final equations or the end answers for a given problem will be same. And one more data is given here, which is very much required to solve this problem. The incremental production cost, or you can also call it as the incremental fuel cost of the two plants, are given as dF1 by dP1 is equal to 0.025 P1 plus 15. So here you can express this equation as rupees per megawatt hour. And similarly for plant 2, dF2 by dP2 is equal to 0.05 P2 plus 20. So this also can be expressed in terms of rupees per megawatt hour. So the coordination equation here is, so as a part of solution, so first you have to identify whether this problem belongs to case 1 or case 2. So in my opinion, case 1 is nothing but without losses. In my opinion, case 1 is nothing but without PL, without power transmission loss. Case 2 is nothing but consider the losses with PL. So here, as per the problem statement, there is a power loss of 15.625 megawatt. That means this particular problem belongs to case 2, not belongs to case 1. So whenever you think about case 2, that means when you consider the power transmission losses, the condition for economic load dispatch is nothing but DC1 by dP1 into L1, that is equal to DC2 by dP2 into L2, that is equal to lambda. Here I am considering only the two terms because the number of plants given in the problem are only 2. And here to find L1 and L2, you need incremental transmission loss. To determine incremental transmission loss, obviously we require loss equation. So the loss equation is expressed in general for two plant system as PL is equal to B11 P1 square plus B22 P2 square plus 2B12 P1 P2. Here, based on the given system, the complete load is connected at only near to the plant 2 and very far from the plant 1. So that means there is no contribution of power 2 in developing any kind of power transmission loss. So that is, we can conclude that the loss coefficients which involve plant 2 will become 0. So that means B22 is 0 and also B12, that is also equal to B21, is also equal to 0. So this is because the complete load is connected at plant 2. Suppose if the entire load is connected near to plant 1 but not at plant 2, then the loss coefficients B11, B12 is equal to 0. So once you substitute these B coefficient values, the loss equation will change to PL is equal to B11 P1 square. So this step is very, very important in these kind of problems. So now here, if you want to find this loss coefficient, you need loss value and also P1 value. And this information is very much clearly given in the problem statement. A 125 megawatt is being transmitted from plant 1 then this is the loss. 15.625 will be the loss. So you can substitute this 125 as P1 here and 15.625 megawatt in the place of PL. Then you can determine B11 loss coefficient. So once you know B11, then we can use this coordination equation or penalty factor equations to determine P1, P2 and then PD. So once you find P1, we can substitute that same P1 value here and then you can determine power transmission loss also. So this is the procedure or steps how we can solve this particular given problem. So now let me show the solution. So here you can see, as I mentioned, since the load is at bus 2 alone, therefore the losses in the line will not be affected by generator of plant 2. So that's why PL become B11 P1 square, since B12 that is equal to B21 equal to 0 and also B22 is equal to 0. So once you substitute PL value as 15.625 and P1 value 125, then we are able to get B11 as 0.0011 and the unit is megawatt inverse. So let me erase all the formulas here so that you can see the solution in detail. You can see here the B11 value we got around 0.001 megawatt inverse. So any problem, the general procedure is before solving or try to understand the problem first. So once we can understand the problem and the given data, then very easily you can apply the known formulas so that it will be easy to solve any kind of problem. So now let's take the help of coordination equation. So this is coordination equation expressed in a different form. So actually speaking, this can be expressed as dF1 by dP1 into L1 is equal to lambda, where L1 is expressed as 1 by 1 minus dou PL by dou P1, that is equal to lambda. So this particular equation, if you rearrange, it can be expressed in this form. Other than that, nothing is different. Only it has been expressed in a different form. So we have already equation for PL as PL is equal to B11 P1 square. So once you differentiate this equation, we can express dPL by dP1 as, if you substitute B11 value which we got in the previous slide as 0.001, then it will change to 0.002 into P1, because we have here P1 square. So once you differentiate this with respect to P1, it will become 2 into P1. So 2 into 0.001 will give you 0.002. So now substitute this equation and also dF1 by dP1 equation, which is given in the problem statement, in this coordination equation, then you will get this equation. So if you simplify this, the lambda value is also given in the problem statement as 24 rupees per megawatt hour. So once we substitute all the values here, then you can solve for P1. So you will get P1 as 123.28 megawatt. Now similarly for plant 2, we can write equation as dF2 by dP2 plus lambda into dou PL by dou P2 is equal to lambda. But here there is no contribution in the loss with respect to plant 2. So then by default this dou PL by dou P2 will become equal to 0. Or blindly you can remember that whenever the load is connected near to any one particular plant, that particular plant ITL value will become equal to 0 because both are connected very close to each other. So there is no contribution of this power P2 in creating any kind of transmission loss PL. So that is the reason the ITL dou PL by dou P2 will become equal to 0. So by using this particular equation, now you can express this and you can get the value of P2. So the P2 value we got around 80 megawatt. So now you have P1 values and P2 value. Substitute P1 value in this last equation. PL is equal to V11 P1 square. Then you will get PL as 15.19 megawatt. So once we have individual unit power output values and also power transmission loss values, now take the help of power balance equation. So what is power balance equation? The total power generation PG should be equal to total power demand plus power transmission loss. So here we have two power plants, P1 and P2. So the total power generation will become P1 plus P2. That is equal to PD plus PL. So from this you can write the power demand you want to find. So PD will become equal to P1 plus P2 minus PL. So using this particular equation, you can get the value for PD as 188.1 megawatt. So all these steps are by using the first approach, that is by using coordination equation. The same problem is also asked to find by using penalty factor method. So now let's see the other way of representing the same coordination equation, that is called penalty factor method, and get the values as similar. So this is the solution by using penalty factor. So first let's find the penalty factor of plant 1. So penalty factor of plant 1 is indicated as L1. L1 is equal to 1 by 1 minus dou PL by dou P1. We already have dou PL by dou P1 equation as 0.002 P1. And now you can substitute this L1 in the again coordination equation, that is nothing but dF1 by dP1 into L1 is equal to lambda. So by using the same equation only, we can substitute here this L1. So from this again you will get the same value P1. So that's what I mentioned at the beginning. Actually speaking, there is no much difference between the coordination approach, coordination equation approach and penalty factor method. So both are same only. The only difference is how you are proceeding, how you are representing that particular equation is little different. Other than that, the values and everything will be same. So as I told that the complete load is connected very near to the plant 2. So that's why dou PL by dou P2 is by default equal to 0. So then the penalty factor will become 1. Because we have a formula for penalty factor of plant 2. L2 is equal to 1 by 1 minus dou PL by dou P2. So once you substitute this incremental transmission 0, then you will get the penalty factor as 1. So from the next time onwards, directly you can represent that whenever the load is connected near to any one particular plant, that particular plant penalty factor value will become directly 1 and ITL value will become directly 0. Now again by using the coordination equation for plant 2, that is nothing but dF2 by dP2 into L2, that is equal to lambda. By using this equation, if you substitute all the values, then you will get P2 as 80 megawatt. So once you got P1, P2 values, you know very well, use power balance equation to find power demand value. So that's about the first numerical problem. Now let's see another case problem, numerical 2. So here, assume that the fuel input in BTU per hour. BTU means British thermal unit. So let me write that here. BTU means British thermal unit. This is the unit to express input energy rate. Of two units, 1 and 2 are given below here. The maximum and minimum loads on the units are 100 megawatt and 10 megawatt. So that means once you determine the values of P1 and P2, so the P1 and P2 values are supposed to be within the range of 10 megawatt and 100 megawatt. So this is the constraint we have to satisfy. Determine the minimum cost of generation when the following load as shown in the figure is supplied. The cost of fuel is rupees 2 per million BTU. That means lambda value is given as rupees 2 per million BTU. This is lambda value given. So two fuel cost equations are given here, F1 and F2. So F1 you can express in terms of rupees per hour, and similarly F2 also can be expressed in rupees per hour. So if you observe the difference between this problem and the earlier problems what we have solved is, in all the previous problems the load demand value is directly mentioned as a numerical value, but here instead of mentioning that load demand value as only one value, here a graph is given. So this is the graph called as load curve. This particular graph is called as load curve. So in the previous lecture, I defined already what is load curve. The load curve is nothing but the graph or curve drawn between the power demand versus time. So the time is taken on x-axis and the power demand is taken on y-axis. And here this particular load graph will represent a real scenario. That means the load demand will never be constant in the real scenario. Here if you observe from 12 midnight to 6 a.m. the load demand is around 50 megawatt. And again from 6 a.m. to probably this is 6 p.m. So up to 6 p.m. the load demand is again 150 megawatt. And then from 6 p.m. to next up to 12 midnight, the load demand is around 50 megawatt. So here you can observe there are two possible load conditions. One is 50 megawatt, another one is 150 megawatt. So that means indirectly this problem is having two cases. In case one, you have to consider this particular load demand, that is PD is equal to 50 megawatt. And in other case, consider this increased load. So let us take that as case 2. In case 2, the power demand is equal to 150 megawatt. So now, if you can solve this problem for only one case, the other case will be similar, except the change is the PD value is equal to 150 megawatt. So in the case 1, here, now first let's try to identify whether this particular problem belongs to case 1 or case 2. In the sense, in my opinion, case 1 is nothing but without losses, case 2 is nothing but with losses. So here there is no information with respect to losses. So that means this particular problem belongs to without losses case. Without losses case. So when it is without losses case, the condition for economic load dispatch, as we know already, that is dC1 by dP1 is equal to. So here instead of C, I am taking it as F, because in the problem the cost is represented as F. So you can accordingly you can change this notation. So dF1 by dP1 that is equal to dF2 by dP2 that is equal to lambda. So now use this equation and use PD is equal to 50 megawatt. So let's say this is equation 1. We can substitute dF1 by dP1, dF2 by dP2. So how to get dF1 by dP1? Just differentiate this first equation. If you differentiate this, you will get dF1 by dP1 is equal to, so differentiation of 8P1 with respect to P1 will give you 8 plus 0.024 into P1 square. So differentiation will become 0.024 into P1 square will become 2 into P1. So it will become 0.024 into 2. So that means 0.048 into P1 plus 80 into 10 power 6 will become 0. But anyhow, for these two terms also, you have to consider 10 power 6. And similarly, df2 by dp2 will become, if you differentiate this particular equation, then you will get it is 6 plus 0.04 into 2, so you will get 0.08 into P2 all multiplied with 10 power 6. So now we have df1 by dp1 and also df2 by dp2. So you can substitute here, and also we have lambda value, that is rupees 2 per million BTU. And at the same time, for the case 1, we can write this total demand has to be supplied by using both units 1 and 2. So you can write based on that statement, P1 plus P2 should be equal to the power demand PD, that should be equal to 50 megawatt. So take this as equation 2. So once you substitute df1 by dp1 and df2 by dp2 in equation 1 and solve this equation 1 and 2 to get P1 and P2 values, that will complete the solution for case 1. So after that, in the case 2, there won't be any change in equation 1. There will be change only in equation 2. So now in case 2, the equation 2 will become P1 plus P2 is equal to 150 megawatts. Now this will become equation 2 whenever you are solving this case 2. So this is how we can solve this particular problem. So now let me show the solution so that you can observe the similar kind of procedure or steps. So let me erase this for better visibility. So any problem, if you know the standard formulas, you can solve very easily. The only thing is you have to understand the concept, and then you should know how to apply all the known formulas. So now here you can see the equations are represented in the form of df1 by dp1 and df2 by dp2. You can see here. So the first case is considered here when the load is 150 megawatt. When the load is 150 megawatt, the economic loading condition is df1 by dp1 is equal to df2 by dp2. So this is the complete solution for case 1. So once you get P1, P2 values, actually in the problem, the cost is asked. So you have to substitute this P1 and P2 values in the given fuel equations F1 and F2. Then we'll get the values for F1 and F2. So here F1 we got around 210.868 million BTU per hour and F2 is 373.5 million BTU per hour. So this is case 1. So now we have to consider case 2, that is 150 megawatt. So this is for case 2 when the load is 150 megawatt. Again we have written condition here. What is the condition here? df1 by dp1 is equal to df2 by dp2. That is nothing but equation 1. So based on this you can express this, and this will become now equation 2. So solve equation 1 and 2 which has two variables P1 and P2, then you will get P1 value and P2 values. So once you get P1 and P2, just similar to case 1, substitute these values in F1 and F2 equations, then you will get F1 value and F2 value. So once you got F1 and F2 values for the two cases, suppose if the question is asked from for the entire duration of time given, what is the cost of generation? Then you can substitute all F1 and F2 values and take sum, then it will give you total cost. It is somewhere around 52,649.61 rupees. So this will complete the entire solution. So now let me show the another case problem. So here, if you observe carefully, the load data or the load information is given in the form of load curve. So the same problem can be modified where instead of representing the load curve in the form of graph, it can be represented in the tabular form. So here also you have to find for the load variations, allocate the load optimally. That means you have to find P1 and P2. And in this problem, there is no information with respect to loss. That means this particular problem will belongs to case 1, that is without losses. So without losses, what is the condition for economic dispatch? It is DC1 by dP1 is equal to DC2 by dP2, that is equal to lambda. But here, one change when it compared to previous problem is, in the previous problem, we have only two different values for the loads, that is 50 megawatt and 150 megawatt. But in this particular problem, we have 5 different values of loads. At each duration of time, the load is keep on changing. So first case, you have to take 50 megawatt. Second case, you have to take power demand as 120 megawatt. Third case, 180. Fourth case, 200. And the fifth case is 80 megawatt. In all the cases, there won't be any change in the equation 1. Only the equation 2 will change. The equation 2 is nothing but the total power generation P1 plus P2 is equal to, if you consider this case first, then it is equal to 50 megawatt. Or else, if you go to next case, instead of 50, you have to take 120 megawatt. And the next case, instead of 120, you have to take 180 megawatt. And in the next case, instead of 180, you have to take 200 megawatt. And in the next case, instead of 200, you have to take 80 megawatt. So now this particular equation will become equation 2. So we have equation 1 and equation 2. So in every case, if you solve these two equations, every time we are able to get the P1 and P2 values. So this particular problem is very, very simple once you understand the given problem statement. So in this lecture, we have seen 3 different numerical problems based on the economic load dispatch. One is with considering losses and the other problem is without considering losses. So once you know the formulas and you know how to apply them, you can solve any given problem. Even if there is some kind of tricky or modification in the problem, you can solve very easily if you understand the concept clearly. Okay. Thank you all. So we will meet in next lecture.